Hello, we're going to look at angular velocity in this lesson, which is part of circular motion. It's all to do with rotation, and so we'll be looking at some examples of rotation first. If we quickly look at the specification, at the start of the circular motion topic we see here down A, B and C reference to the radian as a measure of angle. We're going to look at that a bit later. Most of you will have done that in maths already, but if you haven't, don't worry. We've got a PowerPoint to cover that. Then we'll be looking at period and frequency of an object in circular motion. And then what we're really going to focus on is what do we mean by angular velocity and how do we calculate it. And one important thing we'll be looking at is conversion of different ways of expressing rotation rates. So typically there are lots of examples of rotation in your home. Here's one common example, a washing machine which is in a spin cycle, and you can see here 1400 is displayed, and that's referring to the spin rate of 1400 revolutions per minute, or 1400 RPM. And it's a very common unit to see. We might have rotation rates in car engines which are very high, thousands of revs, but we also have very slow rotation rates, which I'll be showing you one or two in a minute. Before we do that though, think of in your own home there are lots of electric motors that cause rotation of one thing or another. So what I'd like to do is for 1 minute see if you can write down 5 examples of electric motors in your home which may be causing rotation. Press the pause button now, and then we'll come back in 1 minute. Okay, how did you get on? So let's have a look. There are a surprisingly large number of electric motors in the home. Oven fans and food processors, quite common. Within your fridge and freezer there's a pump that pumps refrigerant around to keep the fridge cool. And then all the other examples are fairly common. You'll no doubt realise that most of these are in your own home. Perhaps not so common though, this is something I've got at home which I've been using for several years to do with photography, and I'm going to quickly show you a video that was recorded a few years ago using our telescope at Basvik. So here we've got an image of the moon which is slowly coming into view. And this was taken by pointing the telescope at one point in the sky and then just allowing it to record. And it clearly looks as though the moon's moving across the screen, but in fact this is caused by the Earth's rotation. And this is quite interesting to see, but it could be a problem if you want to take an image of an object. If it's not staying still, then you get a blurred image if you're taking a still. So one device that a lot of astronomers use who take photographs is they have a device which keeps the telescope moving at the same rate as the Earth is rotating. And this motor that I'm pointing at here is one such motor. It rotates, there's a cog here, one full cycle every 24 hours. So if you were to look at it, you'd hardly notice it was moving at all. But the rotation rate is so that your telescope keeps pointing at the same star for long periods of time. So when we talk about angular velocity, what do we actually mean? Angular velocity is measured in radians per second. The way we would calculate it is we would measure a change in the angular displacement over a change in the time for that angular displacement. It's a similar idea to when we looked at linear velocity. We were talking about the rate of change of linear displacement. With angular velocity, we're talking about the rate of change of angular displacement. The angular velocity is measured in radians per second. We write the radian as rad, and then s to the minus 1, and then this familiar rad and seconds for time. If we were looking at how this would look in terms of circular motion, we've got on this diagram 2 red arrows which refer to what we call tangential velocity. This is the velocity at an instant as an object moves in a circular path. What we're referring to with angular velocity is how much this angle theta changes per second. And so the way we do that is we work out what the angle is in radians and how long it took for that angle to sweep out. So down here, delta theta over delta t gives us the average angular velocity, and we assume that the rate is remaining constant. If we know the frequency of rotation, how many times per second the object is rotating, then it's a simple matter of multiplying that frequency in hertz by 2 pi to give us the angular velocity. We have two other equations up here which we'll be using more in circular motion when we get onto that part of the topic. Typically in this topic you need to do several conversions. The commonly used RPM will always need to be converted to radians per second if you're going to use omega in an equation. And so to do that, over here, to calculate the angular velocity, we take the RPM value, we multiply it by 2 pi and divide by 60. The inverse operation to go from omega to RPM would simply be rearranging the equation above. So we get RPM equals omega over 2 pi times 60. From frequency to omega, as we just saw on the previous page, omega equals 2 pi f. And from frequency in hertz to t in the period in seconds, frequency is 1 over the period. There's a short exercise after this, giving you a chance to practice these conversions. And it's important that you really get on top of this, because as we move on to the later parts of the course, in circular motion, you'll see that omega appears in a number of other equations. And so it's really important that you get completely on top of this at this stage. Okay, thank you.